You utilize them for some purpose or another. I think for Excel it may be helpful to kind of go through it. Yeah, I hope so. That's why I keep on religiously putting those up to make sure that you have access to them. You're welcome. So there are different ways to access them. So you can go on Zoom, you can do those links. If you look on the tab on the left, you see the different tabs, and one of them is Zoom. You can look them up there. Yeah, but you know the hang. You know how to approach this on Canvas. Okay, hypothesis testing with set tests. So we talked last time about set scores and standardization, if you remember. That was a skeptical look. Okay, so we talked about standardization of the normal distribution curve. And this is important to know and to understand, because this is literally the portal into what we will be discussing today. So again, as a recap, we are standardizing raw scores from a population by essentially taking the raw score, subtracting the mean, and dividing it by the standard deviation. As a consequence from doing that, we're basically getting the individual score expressed as the number of standard deviation is located away from the mean. So when you calculate the difference between an individual score and the mean, and you divide that by the standard deviation, you get exactly that distance expressed as the number of standard deviation. And that is true for whatever variable you're using it, under the assumption that it's a normal distribution curve. And the beauty is really that you can, in a fair fashion, compare different variables. If you remember from last class, we looked into emotions and the emotion of disgust and the emotion of fear as a time series plot over the 20th century. And that has changed tremendously in all three parameters. It has decreased tremendously as a function of time. So now, why do you do that? Because all of these three parameters had different matrices. So you measure fear with a survey, it has a different metric than disgust, has a different metric than all emotions quantified with whatever survey you use. So you basically, you're taking all the entries you have for a population and you're standardizing it as per the mean and the standard deviation. Thereby you get a distribution of these set scores. You get a distribution, a standard normal distribution, and you can express this for each year. And you have a comparison of these three variables, although they're not on the same scale. And that is the beauty of utilizing set scores. In addition, you get with the set score distribution table a wonderful tool that allows you to understand your normal distribution in more detail. So we remember that the normal distribution is symmetric, bell-shaped, and unimodal. That means where the mode, mean, and median is located, which is right here, the highest peak, you separate this normal distribution curve in the lower 50% and the higher 50%. Ergo, a set score of 0, where you're subtracting the mean from an individual score you're interested in, if that mean and the mean, so if you calculate for mean, it's going to be 0, and at 0, this is 50%. So you have exactly there 50%. The number of standard deviation you go downwards, you're diminishing the proportion of the population that is lesser than this particular entry. So if you go one standard deviation to the left from the mean, and you go to -1, set score of -1, you're subtracting 34% from it. And this is depicted in this graph, if you remember. You can standardize your normal distribution curve by having 34% between 0 and -1, 34% between 0 and +1, which leads us to the so-called empirical rule that you have between -1 and +1, 68% of your population. Between +2 and -2, you have 95.7% of your population, because you have an additional 14% here between 1 and 2. You have an additional 14% here between -1 and -2. If you go for 3 standard deviation and you have altogether 6 standard deviation of an interval, you basically get 99% of your population. And this is important because today we're gonna go a little deeper into this, because you can utilize this information to quantify certain intervals, certain parts of the normal distribution, depending on what you're interested in. So if you want to know what percentage of my population is below a STAT score of 0.98, I know that from 0 to infinity, a little note, actually, I didn't mention this last time. There was a question that came up in the previous class. This is an asymptotic function. That means this function is never touching the x-axis. It will meet the x-axis in infinity, but never on a measurable scale, on a measurable value. So now we have this function basically defines now this area under the function and this area under the curve. So now you're basically quantifying everything less than 50, everything less than the mean will be 50%. From 50 to 0.98, that's 33.65%. As a consequence, you can conclude that 83.65% will be less than 0.98 STAT score. The calculation of this is, let's assume the example that we have a population of New York City and we have blood pressure measurements of every single citizen of New York City. And the mean is 130 and the standard deviation is 10. Let's make it simple. So that means that 0.98, that will essentially be 139.8 millimeter Hg blood pressure. Because it's 130, that's the mean, plus 0.98 multiplied by 10. So that's 139.8. That's how simple the calculations are. So now plus 1 would be 140, minus 1 would be 120, right? What percentage of the population is between 140 and 120? It's 68%. That means you can quantify the proportion of the population that is between two values that basically you can calculate back and forth. You can convert it to a STAT score, you can convert it in a percentile. You can come from a percentile. If I want to know 25% of my population is below which blood pressure value, I basically go into my distribution table. I look for 25, which is somewhere here at 0.6, was it 0.68? That's 25. And I know if I go for, let's say 0.68. 0.68 multiplied by the standard deviation, that is essentially 6.8. So 130 minus 6.8 is 123.2. So I know now that 25% of my population has a blood pressure less than 123.2. I also know that when I draw a random person, I stop a random person and I pull out my blood pressure meter and I start measuring that poor person, I have a 25% probability, 23.2% probability that this individual will have 25% probability that this individual will have a blood pressure less than 123.2. Sorry, it's late. That was longer. Makes sense, right? So you have a proportion, you randomly draw a person, that probability will be consistent with the number of people with a certain condition, with a certain feature, which is a binary feature. It's either it's less than 123.2 or not. Make sense? Good. Law of large numbers from the probability class. Good. So now back to this. So that's the distribution table. So you have this association. This will never change. This is for normal distribution. You standardize them always the same way, and you can make the same relationships between probabilities, proportions of a population, probabilities in hypothesis testing. These associations never change. But the only thing that changes is the mean and the standard deviation. But the association and the utilization of these two markers will not change. So we know now that 83.65% are less than 0.98 of a STAT score. If I want to know now what proportion of the population is higher than that, I need to calculate 100% because that's the universe under my function. That's 100%, and I know now that 83.65% are less than that value. If I calculate 100 minus 83.65, I know what proportion of the population is greater than that value. Correct? Makes sense, right? So equally, I can calculate now the proportion of individuals between 120 and 140. As we've done before, blood pressure. 130 is the mean, 10 is the standard deviation. I know 120 to 140. I know that 120 would be -1. At -1, I have 15.87. As seen here, 15.8.7. If I go to +1, I have here 0.8413. 0.84 minus 16 or 0.84 minus 0.16 is 0.68. So that's 68%. So that's the 68% with one standard deviation, empirical rule. So, but this relationship does not change and allows you to basically calculate proportions above, proportions below, and proportions between an interval. Both of this will be important. So this is the example now that we want to utilize. So we have now 0.98 and minus 0.98. That's our 16.35. And here we again have 16.35. So that's 32.7. That means that 67.3% of my population is here between minus 0.98 and plus 0.98. So now we have the example here, a different example, different use case. So Manuel is a student in, I don't know which grade, and he's not as tall as his colleagues. That means he has a rather extreme height. So if we measure Manuel's height against the population of interest, which could be his classmates, could be all the students in the school, could be all the students in New York City, could be all the students in the US. He basically, his height, let's say he is 5.2, 5.1, whatever. Calculating this 5.2 minus the average of, let's say 5.6, puts him on a STAT score of minus 1.82. That means that to the left, we have 3.44 percentile. So we have 3.44% of that population that we have compared Manuel to will be smaller than Manuel. That essentially means in the inverse that 100 minus 3.44, that's 96.56, will be taller than Manuel. If we were to quantify the individuals with a height comparable in its extremeness, we would need to take the 3.44, keeping in mind that the normal distribution is symmetric and basically mirror this to the positive STAT scores. And we say, okay, so we have 3.44. So Manuel is a little shorter, and basically 3.4% of his of the fellow other students will be even shorter than him, as short or even shorter. But on the opposite end, we're going to have 3.44% of students that are taller than a corresponding SAT score. Makes sense, right? So it's symmetric, it's positive and negative. In that example, so keeping this duality of negative SAT scores and positive SAT scores in mind, if you were asked to calculate the sum of all numbers smaller than 10, what would be your response?
You know something we don't?
I don't know. What's the number? What's the sum? Somebody. Nobody wants to see it. So there are two different ways how you can approach this. The simple way is to calculate it, right? There's like 10 and 9, 19, 27, 27, 33, 38, 42, 45. I actually miscalculated. So the correct answer is 55. The complicated way is complicated because you basically trip like 26 times on the way to calculate that. Because you're referring to a previous value, you carry that forward, and then you add a new one. There's an easier way because it's about symmetry. Symmetry means that you have a value on the smaller end and a value on the upper end. And if you add up, so you have 1 to 10, you add up 1 and 10, you get 11. If you take 2 and 9, you get 11. If you take 3 and 8, you get 11. You take 4 and 7, you get 11. If you match them up symmetrically, you get sums of 11, and you get exactly 5 pairs. 11 multiplied by 5 is 55. If you do that with 100, you have 1 and 100. You have 2 and 99. If you do that with 1,000, you have 1 and 1,000. So you can do this with any random combination that you want to think of. And it always comes to the same end. It's always the same result, essentially. So you either sum them by hand, or you do it as the pairwise approach. The person who invented that was apparently stating this as a child as the most preferable approach to approach this. So he came up with the same kind of version how to calculate that. But he invented that, and his name was Gauss in the 18th, 19th century. I'm not sure, not a historian. So, but basically keep this symmetry in mind when thinking about things, because we will in the following we will look at two-sided hypothesis testing. So we're testing values that are more extremes than these symmetric thresholds. So everything beyond the threshold will serve our hypothesis test. That's why I came up with this example, and that's why I wanted you just for a second to take a step back and to appreciate that power that symmetry actually has mathematically. Good. So this was essentially the 3.44. So these are values as extreme as Manuel's height and smaller. Then you have that other individual that's at 1.82 positive SAT score. and everybody who is taller. These are the extremes in the distribution. Yeah, the attractive person rating, I'm not really understanding. Those of you interested can read it up in the book. So we have the same exercise here. So you can, with a STAT score of 0.33, if we would use this, for example, for our blood pressure example, we have a mean of 130. We have a standard deviation of 10 with a STAT score of 0.33. We basically get a set that translates into blood pressure of 133.3, because sigma multiplied by the STAT score plus the mean will basically get you to the raw score. So it always follows the same principle. It's super simple arithmetically, but conceptually it's gonna get a little bit trickier now. So now here, when we're coming to the distribution of means, I wanna go back to our slides from last time, because the central limit theorem that we discussed last time requires here a little bit more thought. So if you have, and these are the happiness scores you remember from last time. So we have here individual scores from each country that was in our spreadsheet. Each of these countries contributed one value. If we are sampling and building samples from our country, and we basically have samples of 5 or samples of 10, we get a mean happiness score for this sample that we have studied. If each of these entries here is one sample, the distribution of sample means becomes slimmer, and the mean estimate of our population, which we know from the individual scores was at 5.3 or so. So that's here the mode, that's the highest peak. That is our mean, will be more accurately reflected by our means from repeated random samples. So basically each sample that you draw, each mean from each sample will contribute an estimate of the mean. And in its totality, you do that 100 times, you will get a fairly good estimate of the mean by looking at the mean of means. So you get all these means to build a distribution. This is going to be slim, and it will be converging towards the mean of your population. What we, in addition, have to this variability around this mean estimate from all your samples will follow a distribution that is defined by the so-called standard error of the mean. The standard error of the mean is calculated as the standard deviation of your population divided by the square root of the sample size, which means if you have a distribution, let's go back to the blood pressure example. We have a blood pressure in New York City that has a wide variability. If the variability is even wider, your standard error of the mean will also be wider, because you're drawing now small samples. You draw samples of 30 and you draw like hundreds of them. Let's say you draw 100 samples of 30 from the population of New York City. You get 100 means. You have a certain variability of means around that mean of all means. And this variability will be affected by the variability of the individual blood pressure measurement in your population. Because if you have more variability in your population, your variability of the means will also be wider, because your sample could hypothetically be drawn from the extremes in your populations, because it's just much more frequent to have extremely large values that are deviating much from the mean. So variability affects in an inverse positive fashion, not inverse, in a positive fashion, the standard error, the variability of these means in a distribution of means. If you have now large, and so this is the numerator. If you look at the denominator, you have here the square root of the n. The square root of the n basically will lower this variability, because the larger your sample, the less variability you will get. And the more accurate the reflection of the population mean will be by the estimate from your sample mean. It makes a difference in terms, if you want an accurate reflection of the blood pressures in New York City, or the mean blood pressure in New York City, and you draw a sample of 30 as compared to a sample of 1,000, your estimate of the mean blood pressure with the 1,000 people will be more accurate, right? It's logic in a way. So the more people you sample, the better your estimate becomes. And that's why this is in the denominator and lowers the variability of these sample means around the mean of means. So that makes the distribution of the sample means narrower. So this is basically this appearance. So you have here the distribution of the individual scores here in orange. So that's the blood pressure in New York City. And then you have these estimates, this hypothetical mean of means and this hypothetical random samples that you have drawn that basically appears in a much slimmer format because it's a much more accurate estimate of the mean as compared to the individual scores. And the relationship between those two, that's the standard error of the mean. That's the division of the standard deviation from the orange by the square root of the n and getting it to the standard error of the mean. That essentially is, that essentially is the so-called central limit theorem. And why is this important? Because in the following, you want to calculate a STAT score. And this STAT score is actually not the STAT score, that's actually more of a STAT test statistic. Because what you do, you take that mean of your sample and you subtract from that mean your population mean. And you're dividing it now through the expected variability of your means. So you have these 100 samples, you have a certain variability of these sample means that you have seen in all your different samples, and this will affect your STAT test statistic. In essence, it will affect it to an extent that you can now make conclusions about the probability that your sample that you have drawn, your sample mean, is indeed different from your population mean, or it's just different numerically by pure chance. So you can, based on the formulation of a null hypothesis, where you say there's no difference between my sample mean and my population mean. You remember null hypothesis, no difference. Research hypothesis, there's a difference. If I am now testing the null hypothesis, and I find a STAT score as extreme as those constituting only the outer realms of my normal distribution curve of this distribution of differences. And I standardize this and I find a STAT score that is exceeding what I'm willing to accept as an error, then I would reject my null hypothesis. So what does that mean? I have here some other slides that I want to show you in this context, which I think is showing them a little better. So essentially you have, let's say you have a mean blood pressure in New York City of 130, or actually let's stick with that example. We are having, okay. We want to quantify now if hypertensive smoking men in the US have a different cholesterol level as compared to the general population in the US. The cholesterol level in the US is an average 211 milligrams per deciliter. 211 milligrams per deciliter. So here you have 100 milliliters. Those of you that are in chemistry or physics majored will know that deciliter and milliliter can be converted. So it's 200 milligrams per deciliter that we're looking at. So under the null hypothesis, we're saying that the mu, that's our sample mean in this context, equals 211 milligrams per deciliter, which is the US average. The research hypothesis says that our sample mean is different from our population mean. So that corresponds with this expression of the null hypothesis and the alternative hypothesis. So We're not doing one-sided hypothesis testing for now. But when we're testing this now, you have a situation that you are now standardizing that difference between your sample mean and your population mean. This difference, you're standardizing using the standard error of the mean, which is the variability of the means in your distribution of means. Because you're subtracting, in the end of the day, you're subtracting your sample mean from a population mean, the population mean being a constant. It's the same for all sample means that you hypothetically may have in your distribution of means. So it comes to the same thing. So you're standardizing that difference. And now you want to know whether that difference that you have calculated falls into these extreme regions and is therefore not a coincidence and not just due to random sampling, but is indeed a systematic difference between your sample and your population mean. So you're using now your distribution of the sample means to transform this percentage that you have from your set score into a probability of your null hypothesis actually being true or not. So when you have a p-value that is 100%, you're 100% certain that your sample mean and your population mean is identical. So that would be if you would hypothetically have no variability and you're just comparing, you collected the entire population and you calculate population mean minus sample mean and they're identical and they have no variability, then this will be 0. So that will transform into 100% probability of this being not significantly different. So with an set score that goes more to the outside, you are quantifying the probability of you making a mistake. And this mistake is the so-called type 1 error. And you're quantifying the probability to make a mistake when you reject the null hypothesis. And the smaller this probability becomes, then at one point you will define the so-called alpha, upon which you're actually less than your alpha convinced that you actually need to reject the null hypothesis and assume a difference between the sample mean and the population mean and not make a mistake. So this is the so-called type 1 error. Type 1 error is also labeled as a false positive. That means you're rejecting a null hypothesis that you should not be rejecting. Whereas the other dangerous product of the type 1 error is the type 2 error, because the type 2 error is where you're basically not rejecting what you should have rejected. And that is conceptually important to keep in mind. But right now, we are quantifying a type 1 error rate, and we're defining that threshold upon which we are saying this is a type 1 error. So this is the alpha that is mentioned here.
Which one's more common? Which one's more common? Type 1 or type 2? Or are they just...
It depends what you're looking at. So type 1 error, well, according to Nolan and Heinzen, there's actually a high prevalence of type 1 error, because the type 1 error will associate with a set score of 1.96. That's 5% that's commonly used for this probability. And so you find a high prevalence of studies that are reporting something that is consistent with a set score of 1.96, thereby suggesting that it's more common to actually do a type 1 error, because people try to subset their data and massage their data until they pass that threshold and they have something that the journal would actually publish. Is true, I would think, in many cases, but then you also have type 2 errors you have quite often in small studies, where somebody just studied a convenient sample and they did some observation on them that is not adequately powered, and they don't find the difference and they're not reporting it. The problem with type 2 errors is they're likely not published. They're not being published. So speaking of which, is actually a nice point to mention that there's actually nowadays a journal that has actually focused on publishing negative findings. Because nowadays, when you send your article to a journal, you want to show there's a difference and my intervention made a difference, and that actually is a very significant finding. If it doesn't have a significant difference, you may be inclined to just put it in a file drawer. So this being said, the published, in terms of published, it's likely that type 1 error is more often published than not. Yes, please.
Is there any way to get like a document and then like a key of what each letter means?
So you have that in the slides, right? It's all outlined in the slides.
Right. Is there like a one sheet with everything or?
No, there's no sheet. Okay. But you can develop one. Right. Please share it if you develop one. I would love to have the sheet. Good idea. Okay. So all right, so we have a set statistic for a group is basically quantified as this distribution of means. And this distribution of means is basically then utilized for hypothesis testing. We're doing a null hypothesis. We're having a significance level of an alpha. We're calculating now a standardized distribution of means. We're calculating a test statistic. We're calculating the mean of the sample minus the mean of the population divided by the sigma divided by the square root of the n. Thereby, we're getting a set that is reflective of the extremeness of this difference. So basically, it standardizes it. The outcome will be a set score that characterizes and kind of locates this difference on the distribution of differences. And if this is exceeding what we have defined as our critical value, our critical set score, if it exceeds that, we will reject the null hypothesis. And we're doing this now by calculating our p-value. So this is done with this formula that I just showed you. And here's the example. And I want to get an example. I believe in hands-on. So we have our US cholesterol mean of 211. We have a sigma of 46. That's our standard deviation. So now in step 1, we're basically building a null hypothesis. We're defining that there's no difference between the sample mean and 211 milligrams per deciliter. Then we have an alternative hypothesis where this is unequal, and we're defining an alpha of 5%, 0.05. That corresponds with a set score of 1.96, as we have just seen in the slide from Nolan and Heinzen. So let's assume 2 scenarios. We want to do this two-sided. That means a two-sided test basically considers both extremes. Considers the tail to the right and the tail to the left of our differences. A one-sided test has a one-sided hypothesis, is either larger than a certain value or smaller than a certain value. I'm not going to go there now. Let's stick with the two-sided for now. So we have a random sample of 25 hypertensive male smokers, and the average cholesterol level is X. And X bar is here defined as either 195 or 227. And we're comparing this to our population average of 211. How are we doing that? So I showed you the equation, right? So the equation is X bar minus mu divided by the standard error of the mean, which is sigma divided by square root of the n. So we have 195 as our first hypothesis, minus 211 as our population mean, divided by 46, which was our sigma, divided by square root of 25. Simple equation, right? Not complicated. The outcome of this is a set of minus 1.74. And now it's getting a little tricky. So we have now minus 1.74. So we're going to the negative z-score, and remember how to read that, right? So we have in the rows, we have the first decimal from 1 to 3.4, and we have in the columns, we have the second decimal. So minus 1.74 would be located, that's minus 1.7, that's minus 1.71, minus 1.72, minus 1.73, minus 1.74. It's 0.0409, which is identical with what was described here. It's rounded. So this is basically, that z-score is somewhere here and here. It's symmetric on both sides. So that accounts for the negative 1.74, and that's the definition of two-sided. So you check for both extremes. So you have minus 1.74 and plus 1.74. And that essentially is now being multiplied. So you find the corresponding p-value, the corresponding percentage, and you multiply that by 2 because you're accounting for both tails. And that is 0.041 multiplied by 2. And that gives us a p-value of 8%. We defined our alpha as 5%. So our type 1 error risk is larger than the alpha that we're willing to accept. Ergo, this is not significant. Yes?
Multiply by 2 because it's symmetrical?
Exactly.
What do you do with it though?
Well, right now, so you dichotomize it. You would now conclude that there's no significant difference between that sample that I have drawn to the population mean. So now with 25 people out of a population of 420 million, yeah, I wouldn't be too confident of that result, right? So basically, this screams type 2 error in my face so loudly I couldn't agree. I couldn't ignore it, right? And that's the type 2 error. This is causing a type 2 error because you may have in your tiny little sample of 25 people that you randomly found in your unit, you have just a sample that may just be so variable, that may be so biased in its nature, that's not generalizable to the US, that you're looking at a type 2 error. So that's one of the most common reasons for the type 2 error is just an inadequate sample size. So, okay, 8%. So what happens if we're finding now a second sample and the mean cholesterol in the second sample is 227? $227 would be 227 minus 211 divided by 46 divided by the square root of 25. And that would be plus 1.74. So that is where symmetric is important to keep in mind, right? Because it goes in the same direction. The result would be exactly identical. And that's why I came up with the pairs from 1 to 10. That's why I keep on talking about values that are as extreme, because in both directions, it's the same relationship. What's getting now a little bit more interesting is, where this is getting a little bit more interesting is when I do a one-sided test. Because what happens now? So now again, the 195. If I have 195, I only calculated in one direction. That means I am only interested in that mean that is smaller than my 211. So I'm only going in that direction. Consequently, my p-value here is 4.1% or 0.0141. Now I do not multiply it by 2 because I'm only interested in everything that's less than that. So now the null hypothesis is rejected. If I do this in the other direction, I'm interested one-sided again. I'm interested in Is my mu greater than 211? Then I take my 4% and I subtract them from 100%. Then I'm interested in everything above that. So your research hypothesis here defines in which direction from your extreme value you're actually quantifying that area under the curve for. And that's important conceptually. And we will practice this a bit. I have a couple of examples, and that one particular example that emphasizes it nicely. So why would you do a one-sided hypothesis test? If you have a hypothesis that is directional in nature, when you have something that just keeps on growing and growing and growing and will never get smaller, and you want to test this against something else, like I'm saying growing, 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 and not shrinking. It could be like, for example, you have a sample of children and you measure the height over time, right? Like, I think it's rather a rarity that you have a child that's, yeah, okay, let's not go into details, but like, yeah, it's growing. So yes, if you have a directional hypothesis, then you will use one-sided testing. But to be honest, you will need to have a really good justification to get this in your paper. And the statistical review is not going to be pleased with you. So you will have some really good arguments to get that through. So it's a rarity. I don't think I have not seen many papers, and I've read a lot of papers, but I have not seen many papers that have used one-sided hypothesis. Maybe in some ancillary analysis, but it's not a mainstream analysis. Good. So this is basically how you would approach this. And this is hypothesis testing. So now this is a very nice overview. And we will see that from Nolan and Heinzen too. So now we have quantified that p-value. The Drew, I think you have brought it up like 3 classes ago or something like that. This is the p-value. It's the probability of something being as extreme for a true reason, or just being as extreme because of a random sampling error. Or not in the error, just chance. Just as a coincidence, we have sampled a group of individuals of hypertensive smoking males that had a cholesterol level that was as low as 195. Given that smoker with hypertension likely have some lifestyle-related reasons, you would not expect that cholesterol to be lower than the average. But that's a different conversation. Okay, but based on our alpha, we're defining now a p-value which we're willing to accept, and which is our type 1 error cutoff. So now we essentially, once we have defined that alpha, we have now null hypothesis indeed true. And we have a result of our test. So we're rejecting if it's smaller than 5%. So we're rejecting the null hypothesis. If this is indeed true, you're not making an error. That would be the power. So this is this cell here. So null hypothesis is false. You're rejecting a null hypothesis. This is correct. If you have a null hypothesis that's true, and you fail to reject the null hypothesis, again, you do not make a difference. You do not make an error. So that's again true. And you have here no error. The probability is 1 minus alpha. We will get to know that next class on Monday, because that's the confidence interval. If we have no error, and the probability, this probability is 1 minus beta. And we're getting to how to calculate. Now we're not doing this in much detail, but the beta is basically 1 minus the beta is the so-called statistical power. And that statistical power, because it quantifies the probability of not making an error to reject something that actually should be rejected. This power is basically utilized for the design of trials to determine how many people do I need to study and recruit into my study to essentially make correct determination. Then I have type 1 error. So that's basically I'm rejecting something that I shouldn't have rejected, and then I fail to reject something that I shouldn't have, that I should have rejected. That's the type 2 error. The nomenclature of false positive and false negative, I highly recommend to pay attention, because false positive is rejecting something that shouldn't be rejected. False negative is to not reject that you should have rejected. Good. We're not talking much about power. Yeah, we don't need to go over those. Okay. Yeah, we don't need to talk about this. Okay. So this is set statistics for a group. So you're calculating now those that are as extreme. We talked about the steps of hypothesis testing. We talked about step 1. So as the very first thing, you identify the population. You need to understand, okay, so what is my sample? Why do I study the sample? What do I compare that sample to? That's also for you, if you read the question on your quiz, or you, wherever you're exposed to statistics, first read the questions, understand the population, understand what you're trying to do, and that will lead you to decide which test you're going to use. Then quantify population mean, sample mean, or the means of both samples for one of the sample tests. Understand the distribution, understand the standard deviations, understand which standard deviations are given, make the correct assumptions. And that is important. So the assumptions of hypothesis testing are, for parametric tests, as we are currently conducting them, 3 main assumptions. The dependent variable needs to be a scale variable. The participants are randomly selected, and they are not chosen for a particular reason. And thirdly, the population distribution needs to be normally distributed. It's a parametric test. So test your assumptions. These assumptions come again. So the difference between a parametric test and a non-parametric test is in principle based on these 3 assumptions. So we're only gonna discuss, we will only be discussing one non-parametric test, which is the so-called chi-squared test, which is gonna be chapter 17. Comes at like beginning of May, I believe. And that's a fun test, because you're testing nominal variables against each other. So that's a really very powerful test, but it's the only non-parametric test we're actually doing in this class. All other tests basically have as the main underlying assumption that's normal distribution. So identify the population, understand the distribution, understand the assumptions, and choose the appropriate hypothesis test, which is in our case now a STAT test. The underlying given parameters that you will have in a STAT test always the mean of the population and the standard deviation of the population. Notably, of the population. So you know the mu, you know the sigma. That will prompt you to think of STAT test. And right now, this is not really that important to keep in mind. Well, it is important to keep in mind, but for the midterm, you will not deal with any other hypothesis tests than the STAT test. That will be the only hypothesis test on the midterm. For the final, that is cumulative, you will deal with all different hypothesis tests. So you will need to know and read the question and understand, interpret from the question, which test do I need to use? And that's actually quite a tricky aspect of it. That's why I decided to make it a cumulative final, because I think this is, in the end of the day, this is really what's most important, that you understand which test you're using in which use case. Good. Okay, step 2, you're stating the null and the research hypothesis in words and symbolic notation. So we have seen that. We determine the characteristic of the comparison distribution. So in our case, now this is the distribution of the means. So we're comparing this against the distribution of the means. Then we determine the critical values. The critical values are based on the alpha, as we now can quickly confirm. So I told you about the 1.96, and why is it 1.96? Because at 1.96, you have 0.025. And 0.025 multiplied by 2 is 5%. And that's why 1.96 is for an alpha of 5%, the appropriate set score to choose. If you were to use an alpha of 10%, which is done in some occasions, in some use cases, you would go to find here 5%, which is right here between those two. It's considered as being 1.65. It's usually the case. Okay, so this is 10% of alpha. Then we have a 99% threshold. That would be 0.05. So that's where you only have 1%. So that would be 2.575. That would be somewhere here, 2.58. So, but you see, basically, this is where the normal distribution goes slower against the x-axis. So the percentage increments getting smaller and smaller and smaller. So it's 1.65 is 10% alpha, 1.96 is 5% alpha, 2.58 is 1% alpha. When would you choose one versus the other? So two things are to be kept in mind. First of all, if you have large sample sizes, the larger your sample size, the more likely you're going to have a significant result. Makes sense, right? Because you're dividing your standard error of the mean by the square root of the sample size. If I look at the difference in a sample of 200,000 patients, that will be significant. It's almost impossible. It's not significant. It really needs to be so identical that it's not significant. This has a problem on its own right. So that is to be kept in mind. So sometimes with some certain sample sizes, you're well advised, and for some certain use cases, some certain research questions, you can basically alter that alpha. It's in 90% of all research is 5%, and that stems from a research paper by the statistician, very famous statistician Fisher in the UK. He defined that 5% at one point, and that was an arbitrarily chosen threshold according to what I know about it. And based on this one publication where I mentioned 5%, the whole scientific world has embraced 5%. Since then, it's 5% since the 1960s. So it's 5% now. So then you have 10%. You do that maybe with very small sample sizes. Sometimes it's done in genetic studies where you have like rather multidimensional, very small sample size. Then you may use 10%. So there are various use cases where that's okay. And when you have really large data sets, then you use 1%. Then you want to be as strict as possible. Next aspect that is to be kept in mind, not every difference is actually a difference worthwhile interpreting. If you have, if you find in a population of 100,000 people a difference of 1 millimeter Hg blood pressure, don't even bother. It's not meaningful. And this is the distinction between statistically significant and clinically meaningful. Or clinically, in terms of interpretation, meaningful. That can be true for a survey that you have done in 100,000 people, same aspect, right? So you need to understand the magnitude of that measure, and you need to understand, is that actually a meaningful result in the context of your research question? So minuscule little differences in large data sets that are significant may not be as insightful. So keep that in mind. Always question everything along the lines. So statistic is a tool. It helps you to come to an interpretation. And as such, that's how you have to look at it. And not everything that's significant is really helpful. Okay. So we're moving on. Critical values, cutoffs. We found now the 1.96 and the 5%. Now we're calculating a test statistic. That's our set. So that's mean minus population mean divided by the standard error of the mean. And then lastly, we are, based on that set, deciding whether we're going to reject or accept the null hypothesis. Yeah, that's statistically significant, doesn't mean it's meaningful. Example of a set test, one-tailed, two-tailed, we've talked about that, determine critical values. Yeah, so this is where the 1.96 is, it's 2.5% to the extremes. And this 1.96 corresponds with an individual score. That means that these two values of 1.96 have a corresponding value. If you're comparing blood pressures, if you're comparing cholesterol, that has a value. And that value defines your confidence interval. That's just a teaser for Monday. So this is what we will be doing on Monday, basically defining these intervals within which we are 95% confident that our population mean should be located in. So that's kind of the basic concept. You make decisions based on the set, whether this exceeds your critical value or not. And yeah. Okay, then lastly, last 5 minutes, we have harking and p-hacking. So harking stands for hypothesizing after research results are known. Became a verb. So harking is basically, you have a data set, you look at your data set, you see there's a mean, you plot it out and you see like a certain kind of tendency that women, I don't know, women younger than 30 show that dynamic and men above 40 show that dynamic. So you kind of massage your hypothesis, your hypotheses in plural, in the direction to find something meaningful in your data that turns out to be significant. So you basically, you know your results, and then you phrase and form your hypothesis around these results that you can tell the British Medical Journal that you have found the most amazing association ever. That's kind of the idea. So that's harking. So p-hacking is another direction which is unethical almost. It actually is unethical, which is basically where you create little subsets, and these subsets in some shape or form, in some variation, they suddenly show a significant p-value, and you British Medical Journal, there's my paper. So same problem applies. Is a problem because all research, as we have learned with pre-registration, all research should follow a so-called scientific rigor, right? Rigor, how do you pronounce that in English? So this scientific rigor basically asks you to formulate a research question, formulate null hypothesis, and follow your research through exactly in the same shape and form as you have said you would conduct your research. And that's scientific rigor. And not p-hacking and not harking. Good. That's all I had for today. Thanks so much. Have a nice evening.
Thank you.